Hi, I'm Kurt Jordan. I'm an electrical engineer here at Inventus. Today we're going to be looking at RFID tag integration on Tektronix's new mixed domain oscilloscope line. As an embedded engineer, I deal primarily with microcontrollers. I've not really branched out into the RF field. Looking at this now, I can actually go in and buy a canned solution that is an RF package and bring it in and integrate it with my embedded system. We're looking in real time on this scope with the actual spectrum being analyzed in the RFID line and interaction with other digital signals that are occurring on the board. Using this now, I can actually see the signal where before I didn't have access to the actual RF itself. So now I can actually get in and make sure that I'm transmitting what I want to see. I'm getting the response back through that, and I know that I'm not leaking any signals outside of my device. Beforehand, I had to just go and hope that it was giving me that based on a basic ground loop antenna through an analog signal. Now I can actually make sure I'm on the right carrier frequency. I am right there in that money spot to get the actual signal to the tag that I want to see. We're actually looking at the interrogation of the tag from the RF spectrum. Okay, so now we're actually going to take a look at the signal. So first we're going to arm the scope to get ready to capture the signal. Now we'll activate the device and we should see the actual signal be captured by the scope. So we now actually see the RF field, we see the interrogation of the tag, we see the tag response and the digital signal that's being appropriated with it. So now that we have the signal, let's actually add the digital communication that's associated with our electrical signal on top. So we're going to add an SPI bus communication here. So this is actually what is happening from our microcontroller to our RF device. So we can see it decoding the signal right now, and this will actually let us see the actual communication that is happening between the two devices. We can then zoom in and actually see where some of this digital modulation of this SPI communication could be affecting or maybe getting reverse affected by our actual RF modulation. It's actually help pinpoint any types of issue we were having on our RF signal. So now that we have this capability, we're now actually also looking to expand into other wireless ranges. Along with that, we're looking at Bluetooth, along with Bluetooth Low Energy, which is a very hot ticket item on the personal consumer market, along with fitness trackers. So with the fitness tracker that I currently wear, I can take our probe and actually slide it underneath the band and actually be able to capture that interaction with the Bluetooth and actually see the data being put on the screen. So now we've taken the tracker outside of my wristband, and now we can actually see the 3 different frequencies that the Bluetooth is actually hopping from. So if we actually take a single shot capture of this, we should be able to actually see each individual frequency that is occurring. So we can now pan through the device and see all 3 frequencies that the device is actually sending out to try and communicate with a host PC. Okay, so now we've connected to SignalView PC software, so we can actually now control the RF through the scope onto our laptop. So we actually are able to see each individual peak here through time of when the spectrum has changed and see the frequency changing over time in this. And we can see the marker progressing through the software to actually show each individual burst of data that is being put out by the Bluetooth device. So with software from Tektronix, such as their SignalView PC, we're actually able to pull in the data from the scope and actually dive into the modulation characteristics. So we have our 3 peaks. So let's focus on the first burst. So with that, we can actually analyze this in multiple windows and focus in on the actual demodulation of the signal to track what is actually being provided through. So we can actually see the raw data, and we can zoom in to actually see the modulation that is occurring in this frequency shift keying spectrum. Now we can actually focus in and actually track the modulation, so we can see this in a symbol table of the actual raw binary data. We can even go down into the spectrogram and actually see where that is occurring in the actual signal itself, and also see in our constellation map that it is a nice tight signal on this Bluetooth characteristic frequency. Okay, so another wireless technology we're looking at is wireless LAN or Wi-Fi. This is used normally for applications where we need higher bandwidth or higher throughput that Bluetooth is not capable of producing. So here we're actually looking at a live capture of an 802.11 signal, specifically with the G standard in mind. So we're actually able to do a single capture now, so we can actually see one specific instance of the spectrum and also the amplitude over time. So as we scroll through, we can actually watch how the spectrum is changing based on the actual time variant. Now we're actually going to see the advantage of having Signal View PC. So we're going to take this signal and transfer it over to the computer for more further detailed analysis. So now we can actually see and put a marker on the signal and actually watch it progress through and actually see the spectrum change, see it in the spectrogram. So we can actually watch the amplitude changing through time and actually see this burst occurring. So in addition to looking at the spectrum over time, we're able to go down and look at the 802.11 standard from IEEE. Let's focus in on the spectrum emission mask. So this is provided by the IEEE standard for the 802.11 spectrum. This will take us to make sure we are meeting our FCC pre-compliance test. So in addition to looking at the spectrum, we're also able to analyze the modulation to help troubleshoot any throughput issues that may be occurring inside our system. So first, let's focus on a way to measure the accuracy of our modulation, which is the constellation diagram here. We can see with the nice tight clusters that we actually have a very crisp modulation and should not have any throughput issues. So looking at the wireless LAN summary now, we'll actually be able to focus in and look at very specific characteristics of this wireless LAN burst. So inside the wireless summary here, we're actually able to see the error vector magnitude of various fields within our wireless burst. So now we can actually see how, using the new MDO, we're actually able to take multiple devices, put them into one, and see how we can look at RFID, Bluetooth, and wireless LAN, where previously we would have had to have a full spectrum analyzer on the side and an oscilloscope and have to do tricky measurement correlation between the two. Now it's all one time domain. We can see it, analyze it, pull it into Signal View PC, and even do further detailed demodulation of all these signals.